All right, so this is the SpectrumX Data Blitz. My name is Maria Jeleva. I'm in computer science at University at Albany. Let me get to advance this. Okay. So data is critical for spectrum sharing progress. So if you think about, what we need data for, first of all, we needed to be able to make any informed decision about how to use and reuse the radio spectrum. Then we're increasingly talking about different stakeholders sitting on the same spectrum. That requires trust, and trust can only be, supported through, insightful or insight-gleaning data. Research reproducibility hinges on our ability to use and reuse the same data. And then availability of well-curated data is the #1 way to reduce the entry barrier into spectrum research and into spectrum education without having to build a system and run extensive campaigns to collect that data. All right, so data infrastructures have been a core kind of value in SpectrumX. And it shows in all the effort that's been put and the great output that's come out of data-related efforts. So we have a couple of data collection capabilities, the mobile experiment platform being one, and RadioHound X. We have and continue to invest in orchestrated data collection campaigns. So the VLA experiment from last summer and a couple of smaller experiments at Boulder and Madison. We also have crowdsourced data collection campaigns in the Broadband Mapas initiative. We've built out infrastructure for spectrum sharing, spectrum data sharing specifically in the spectrum data system, the SDS, and we have a focus on creating metadata standards for documenting spectrum data, as well as looking into how we can add machine learning readiness into the data that is being collected. So with that, about this session, we have 4 talks that broadly focus on these artifacts that I just mentioned during the previous slide. So the first talk, we'll hear from Mohammed, who will talk about Broadband Mapas with SICAP and the data platform that was built behind this. Then we'll hear about the VLA and the Wisconsin data collection campaign and how the mobile experiment platform and the spectrum data system were used in that process. Third, we'll hear about Starlink data collection campaigns at the MIT Haystack Observatory, and then finally about how those efforts have been used to support student data competitions so that we can, demonstrate as a center how we can lower or eliminate those barriers into spectrum research. So with that, we'll just go through the talks in turn, and then if time allows, we'll take some questions, or we'll wrap up just in time for lunch, and we'll kick it off with Mohammed. And while he's coming up, opportunity to immerse with these data artifacts is tomorrow. We have 2 tutorials, so please plan on attending either, or if you can clone yourself, both.
Thank you, Maria. Hi everyone, my name is Mohammed. I'm a postdoc in Notre Dame. I'm working under Professor Monisha Ghosh, and going to talk about the Broadband Mapas updates and basically general SICAP data platform updates and what data that we have. Yeah, so these are basically the updates that we have right now, the Broadband Mapas crowdsourcing efforts that we have. So we started this from 2022, but right now the latest iteration is data collected from 2025 to 2026. And those are contributed from 4 universities: Southern, Morgan State, University of Puerto Rico, and FAMU. And these are the metadata where we collected the data, and you can see all the US states there. So basically, the center of it, in the 4 universities that I told you is from Louisiana, Florida. So one thing that's not shown is the Puerto Rico, and one in the Maryland. And yeah, those are the number of, on the top left is the number of data that we got, like 1.192 million of data collections. And yeah, these are the cellular data taken from AT&T, T-Mobile, and Verizon, and as well as Wi-Fi data. And also lately we also get the satellite data from the phones. And the data is also tagged, at least we told the students to properly tag the data, at least with the labels outdoors and indoors, so those are very important. And the research questions that we offered the students at the time, so these are credit to Dr. Yasser Ismail and Dr. Fred Lacey from Southern, that comes up with all of these research questions. And those are everything, like you can read it. And I'm hoping that Professor Yasser Ismail is here. He will present the poster on the poster session this afternoon. So lesson learned that we have from running this program MapUs data effort. So basically we first, at the beginning, we established tutorials and methodology. So this is very helpful to get students quickly onboard them to do the data capturing and data collections around the campus or the suburban area, urban area. So we direct them to measure this data. Oh, something like that. And we also implemented feedback from students to improve data platform usability. So we will discuss about this later. And there's some important things that we kind of miss. We need to define the research question early, which we have defined here. And we need to establish a deadline. So, for instance, to present in SpectrumX meeting. So these are efforts that's supposed to get the students engaged. Yeah. So now we're talking about the others, the data platform enhancements, and we're going to dig deeper here on the tutorials tomorrow. And these are, thank you for Peter. Is Peter here? Yeah, so these are the three features that he implemented. So we now have a 4G and 5G band filter. So from the data that we have, we can look up specific LTE or 5G bands. These are very useful for people that wanted to see maybe only millimeter wave deployments where are there in our data set. And then the second one is the CSV band filter, which we use when we export this, when we download this data, we maybe just want to see only part of the data, only data with this cellular band or Wi-Fi bands. And we also added cellular data visualization. As you can see, like these are showing the bands of the LTE and 5G. So these are preliminary tools, so people can just take a look at the data, what bands are there, what kind of RSRP or signal strength that they can see from their data. Yeah, so we also implemented this statistic page. You saw this before, and these are basically the statistics from all of our data. So we already captured up to 18 million data points, and those are the breakdowns over the nations and the U.S. states, all the countries. And yeah, we have like 78 registered users, but I'll talk about it more. And we just starting to track the download requests. So those 15 downloads is maybe like in past months or so. We have more downloads actually, yeah. And these are more statistics. So I'm saying that we out of that 78 users, we approved 66 users because we have this kind of little bit gatekeep the data from the public. So we only allowed it for educational institution and participating industrial people like that are collaborating with SpectrumX. And I counted that there are 24 total institutions that contributed to the data platform. And there are 20, out of that, 20 are educational institutions. And I want to highlight the campaigns that we captured in SIGCAP. So in total, there are 30 campaigns, but these are the highlights. We collected very extensive data on 6 gigahertz Wi-Fi measurements over the University of Michigan, University of Notre Dame, and specifically the Notre Dame Stadium, because we have like very dense deployment, around 1,300 Wi-Fi AP deployed there. And there are efforts to collect multi-cities millimeter wave measurements by Dr. Angie Cruz there. So thank you on that. And in the past, we also have some public sector that are collaborating with us. So in 2021, we did FCC pilot measurements in Colorado, and 2023, we have City of South Bend mobile data measurements. Those are archived in the SIGCAP data platform. And finally, we also have the broadband mappers data from 2022 to the latest. And yeah, I realized that this has some discoverability problem here, so we can only say this in here. I can only promote these data sets here, but we have no this discoverability from the users, so we'll talk about that. It's a future work. And other SIGCAP's platforms, so we did implement some faster geofilter. So anyone who's been using right now, when you're doing filtering data and it's very slow, so we have made some efforts to make it faster. And there are pass bugs that prevented the collection to be ingested in the database. And then we fixed like some minor bugs, and the latest we have this CSV download status page, because sometimes when you download, it says that the status is the data will be sent to your inbox or emails, but we don't know whether the data is processed or is it completed processing. So we are doing that. We're implementing that to show the status. And yeah, so these are the futures improvement that we are planning to do. So right now, Peter is working on the RU project to have a compatibility interface to host other data. So Qualipop here is another app that uses more complicated ways to capture data from phones. And these are separate database, so we want to try to put it into SIGCAP, because SIGCAP itself has a very limit. It has a limit in it that it doesn't show some bands somehow on some operators. And in the future, we also want to investigate integration with SpectrumX data system. So we want to harmonize the SpectrumX data platform, and this might also be a solution for our data set discoverability. And other UX and minor improvement, we have a lot of feedbacks from users, from students, but yeah, we haven't done. We need the funds to fix this. And yeah, I wanted to explore also the public resource on Google Play Store. Those are for ease of installation. Right now, it's basically what we are doing is very invite-only, basically on the app and the data platform. So maybe it will be easier for users to have the data already there, have this app already there in Google Play Store. Okay. Thank you.
Great, thank you. We'll keep questions for the end, and we'll keep moving with our next speaker. So we're going from crowdsourced data collection into targeted campaign data collection, and we'll hear from Ali. Thanks so much.
Hello, I'm back. How does this work? There we go. Okay, so I'm going to talk about two major experimental campaigns that we had within the last year that generated a lot of data on different equipment. So let me give you a quick review of why we have done this. So the 7 gigahertz band has become very interesting recently because different countries are considering repurposing this band for new applications. And one major application is 6G cellular networks. So in addition to reusing the existing 5G bands, 6G is going to use a new band. And WRC has identified 3 bands, and the most promising one is the 7 gigahertz band. So the center has invested heavily on building equipment to be able to transmit and receive in this band, and also we organize and we've conducted all of these experiments over the past year. So the current users in the 7 gigahertz band are weather satellite downlink, point-to-point links, and radio astronomy also uses this band pretty heavily. The interesting thing is that they don't have any protected band here, but they use it on an opportunistic basis because of the current incumbents don't cause much problems for them. So that's basically the current situation, and that is going to change very soon when 6G happens. And 6G is no longer far future. 2030 is now near future. So that's when we expect to have 6G. So as I said, we have organized these different experiments, and I talk about 2 of them specifically because I was leading the active transmission part, where we emulate these 6G phones operating in the 7 gigahertz band. So last year, we had this fantastic experiment at the VLA telescope. This was a joint effort between SpectrumX and TIA and NRAO, and it was great. I really enjoyed it, although I stressed over it a lot as well. So, and then moving to 2 weeks ago, we organized a workshop at the UW-Madison where we study the impact of 6G phones on weather satellite downlinks. And we are planning on an experiment in July. We don't know the detail of that yet. So a quick review of the VLA experiment that happened in July 2025. So the low antenna, blue antennas are basically the 27 VLA antennas. And on the left, we show you basically the 3 different locations or configurations that we use to transmit. So basically, we had the transmitter at location 1, and then it moved to location 2. These are stationary experiments where the transmitter doesn't move. And then in the final experiment that I show as number 3 there, the transmitter was in a car driving near the VLA, because there's a highway going through the VLA, actually. And we're emulating the case that somebody on a phone using the 7 gigahertz band passing near the VLA telescope. While we transmitted from these 3 different locations, we were receiving at these different locations that you see on the right. So we We had 4 of them, plus which are green circles, and a co-located one. And in addition to SpectrumX receivers, NTIA was doing their own measurements, so you see, and also the MITRE company was also doing some measurements. And this is a photo of our hardware in the back of a car. We have a transmitter and a co-located receiver just to monitor what we're transmitting. So this one I didn't show you because it moved with the transmitter. So it was really fun, and I'll talk a little bit more about it in a second. But the second experiment that we did 2 weeks ago, this is basically the start of a series of experiments that we are going to do at UW-Madison. I'm not going to talk about this much because I'm going to talk about it because this was initially my seed fund project that I will talk about more extensively in the afternoon, but just an advertisement maybe for that talk. So what we did, we transmitted from, we had a map configured to transmit from one building that was around 400 meters away from the weather satellite ground station. So this time it's similar to the VLA experiment, but instead of the target system being the radio telescope, now we have a ground station as our target system to study what happens when these phones transmit in the 7 GHz band. How do we potentially interfere with the operation of these systems? So I'm going to talk about this later in the afternoon. So to conclude, we collected a ton of data. That's a high-level message. So we collected tens of terabytes of data on the maps during the VLA experiment and also the UW-Madison experiment. Most of this data, the VLA data is, I think, completely on SDS, and I think we are working on uploading data from the UW-Madison experiment to SDS as well. So in addition to the MEP, our mobile experiment platform, we had some other equipment like spectrum analyzers that also did collect data during these measurements. And during the VLA experiment, the telescope itself was recording data, which is important because we wanted to see basically how our transmissions impact the VLA reception. And then similarly for the UW-Madison experiment, we were collecting data on the ground station. So this was an X-band tracking antenna that would downconvert its signal and send that to a demodulator. We had a split there where we could connect it to a map to see basically the IF signal of this ground station, which was fantastic. I'll talk more about it later. The photo on the right is the first time I saw the impact of the VLA transmitter on the telescope, and I took a photo of it. Low quality, unprofessional, but I like it because that was the first time I saw our signal on the telescope. The message was there. Doesn't matter where we are, even 15 kilometers away from the telescope, our signal was well above the noise floor of the telescope. The photo on the image on the left is the IF signal of the X-band receiver from the UW-Madison experiment. So the bump in the middle is the 6G signal, and there are some spikes you see to the left of it. These are the beacon data signal that we added to the 6G for other reasons. I'll talk more about it in the afternoon talk. But the message here is that even when the antenna was not pointed at us, it was 90 degrees angle or even facing the other direction, it could receive the signal pretty strong. And the transmitter was only 100 milliwatt going to the antenna. So this was very interesting. Again, I'll talk more about it. Tons of data on this and great campaigns. Yeah.
Sally, if you can join the panel and we'll keep questions. Frank, you're up next. Sorry. All right, so Frank will tell us about data measurement focusing on Starlink tracking.
All right. Thank you very much. I'm Franklin from MIT Haystack Observatory. For those who don't know me, I'm Deputy Director for Research for SpectrumX. I have the privilege of working at MIT Haystack Observatory. We're about 45 miles outside of Boston, and we have some instrumentation, usually a little bigger than most people's toys, so it's fun. And for our U students, that's where you're going to be. We're going to get to use all this stuff. We do active and passive sensing, so we have a lot of high power radars. Our typical radars are megawatt hectare class systems. We're very sensitive. Our receive systems are often cryogenic, and so we cover an incredible dynamic range and an incredible range of frequencies between distributed instruments and system capabilities. A lot of what you saw with the MEP came out of a lot of instrumentation work we've done over the years, and work we've done with Scott's group, for example, at CU Boulder. And I'm going to tell you a little bit about data sets that are available. So next slide, please. Or can I do it? I can do it right here? Okay. The green button, oh my God, it's so simple. It's too simple for me. RFI from mega constellations is a rapidly growing issue because there are a rapidly growing number of satellites, exponentially growing. And we are at the start of it. People are in awe of Starlink. It's an amazing constellation. It's one of many that are being planned. And Starship ought to take our launch costs from a few $1,000s a kilogram, which is already an order of magnitude improvement over, say, the space shuttle and earlier launch vehicles. And it's taking it down into probably eventually the few $100 per kilogram range. And that's going to lead to an incredible proliferation of satellite systems far beyond anything we've seen so far. We're not going to be talking about tens of thousands of satellites in a couple decades. We're going to be talking about millions of satellites. And there's plenty of space. If you have 1 million cars and you put them all here on Notre Dame's campus, they're stacked up. You can't go anywhere. It's very crowded. If you put 1 million cars in Texas, you still can drive around. And if you put 1 million cars in all of Earth orbit and then stack them out at different orbital altitudes, you barely see a car except when there's an occasional collision, right? Then you might notice it. There are a lot of potential impacts on radio astronomy in particular that we're very worried about at Haystack. Interference from communications frequencies, unintended emissions. So one of the difficulties is that not everything from the satellites is controlled. So even if they have a license at some frequencies, a lot of times the problem signals are not anything that they were intending to emit. This has been known for a long time. There are sensitivities about it, but nevertheless, the underlying issue is one satellite is almost never a problem, but millions of satellites cannot be avoided. There can be nonlinearity from the interactions with the satellites, and not only your communication signals, but other signals in your environment. Intermodulation products can be the devastating thing that influences systems, especially sensitive systems. We found almost all our systems are starting to get very aggressive filtering in front of all the low noise amplifiers because we simply can't tolerate the interference environments without them. Aggregate interference increases with scale. The bigger your constellation, the bigger your responsibility and difficulties are going to be with dealing with interference. And an issue that is going to become increasingly problematic is reflections from satellites. It isn't just the space emitters, it is everything on the ground that is in a band that you do not intend to come from orbit, but because you've put a reflecting layer up there, you will be able to see it. There's been a lot of work on this. I'll just mention the early LOFAR and MWA work, but we've also started publishing finally some of our work on radio astronomy protected bands, including 1420 megahertz. We've shown Starlink interference. It's not actually just Starlink. It's most satellites interfere at 1420 at a very low level. And then at X-band, lower Ku band, we see transmitter skirt issues with the existing Starlink constellation that exceed the ITU thresholds in the radio astronomy protected bands. We focused on protected bands because it's the only place we actually have any kind of legal basis of a standing, but this is actually at many other frequencies, and it's not always understood. We're working with Starlink to try to understand why this is happening and to give them information to help them resolve it. And it may be amenable to improvements in the satellite. Now, launching satellites costs money, and shielding against electromagnetic emissions takes mass, which costs money, and so there's a delicate balance for satellite vendors on the cost to get their systems into orbit versus their ability to prevent them from emitting unwanted signals. Haystack Observatory, I'll go through our instrumentation really quick. If you want to know more, I can go into a lot of detail. We've done a lot of our work with Starlink with the Haystack Westford telescope. It's an 18-meter class telescope. It's got an extremely broad band, 2 to 14 gigahertz cryogenic receiver. It's got a UHF pedal receiver that my grad student Daniel Shen did for his master's degree that gives us a UHF band capability. We've added an offset feed L-band capability for 1420 megahertz to the telescope. And we typically don't track satellites with this, although we can accomplish it for lower frequencies. It's usually we're operating in kind of a transit mode I'll talk about. And we've taken a lot of data with the system, and I expect this summer we'll get our MEP platforms hooked up and take some RFSOC data with them. We also have a 46-meter and a 68-meter set of antennas used for UHF observations of radar in the space environment. I'll mention that Starlink is not only a problem for their emissions, these are radar returns contaminating our radar data that we use to measure the space environment, and getting rid of Starlink is becoming a full-time job and technical problem. And actually, we kind of know how to do it, but it takes new instrumentation, new higher power aperture radars. So it's a secondary impact is that investments that have been made have to have additional investments in order to be able to continue, national capabilities in the face of increasing constellation densities. We have a lot of UHF data off the system, and we collect historically, we keep some of it. So there is an interesting project in there to analyze what's happened over the last several decades to the UHF band. We also have a 37-meter telescope. This is kind of our capstone instrument at Haystack. It is primarily a satellite imaging radar, which I won't talk a huge amount here. Radar data is simply not available, so don't ask. But the passive data for astronomy and scientific projects, we actually are online finally with scientific capability on the system after it began and upgraded in about 2010, and we finally got the science capability back in 2016. So the radar capability happened a lot earlier. We have 3 RF over fiber channels, soon to be 6 RF over fiber channels available. They typically have 1 to 3 gigahertz bandwidth IFs, depending on the particular band that we want to look at. And right now we're limited at W-band to about 84 gigahertz. And there's work to extend higher frequency there, and not only go higher frequency than that, but go up to frequencies relevant to what we work with called the Event Horizon Telescope, which is a VLBI project. Our digital backends are different depending on the application. For astronomy, we often have low bit depth backends that record very wide bandwidth, gigahertz of bandwidth. We use Edis radios sometimes, and the MEP RFSOC-based platforms are also something we're looking at. But usually, these kinds of systems for astronomy, you're wanting to take gigahertz, multiple gigahertz, 3 gigahertz, 4 gigahertz of bandwidth. We have on campus a medium-rated telescope. A lot of our Starlink data actually at L-band came from this telescope because it's very automated. And it's a 6-meter telescope in the middle of Boston with a really good front-end set that we developed. Daniel Shen and I and our team put this together. And we also have the same feed on the Westford telescope. So a lot of the raw Starlink data and collects and systematic measurements and statistical work we've been doing comes from this system at the moment. We're working to do coincidence detection with Westford so that we can get much higher levels of confidence in the measurements and isolate specific satellites. Now, we often do this by looking at the satellites and dwelling in a position and letting Starlink go through the beam. If you put up any radio system that looks up with any finite beam width that's not too small, you're going to have Starlink go through the beam all the time, like every minute, every couple minutes at most. Wider, lower gain antennas will see Starlink continuously. And you almost always see the side lobes of the satellites. It's continuous now. We had an incredibly hard time trying to get noise-free backgrounds for our measurement campaigns. An example here of L-band, out-of-band Starlink emissions. This is at 1420 megahertz in the radio astronomy hydrogen line protected band. You can see actually Starlink go through in the time frequency spectrogram right there. That's a particularly strong one. Most of these things are relatively weak transits. They're actually, and turns out Starlink's not the strongest one. Some of the Russian satellites are actually really loud at 1420. So this is a problem that's more general than Starlink. It is all these different systems. Our data is usually in digital RF. I have about 80 terabytes on a Haystack SDS to stage data. It is not enough for us to actually put everything up and make it available. And there are often problems with making data available and concerns. So we between our systems have hundreds of terabytes of raw IQ sitting around. I can easily collect more data than anyone here can handle. In fact, we don't have enough resources in SpectrumX to handle the amount of data that we could collect. We have a lot of Westward data that's very interesting, some of which can be publicly released, especially things that look like astronomy. Spectrogram reduction is something we've done for this MRT data, that we have some very sophisticated spectral averaging and RFI removal techniques that have been developed. That pipeline can be run on other data sets and also run on our data sets to systematically reduce them. And I think one of our summer things is going to be to try to get all this into SDS at Haystack. And the Haystack SDS is a target for what we call federated SDS, or the ability to search across the different spectrum data systems. So eventually you're going to be able to find out that data is at Haystack and then request access to it via the SDS federation capabilities that'll come about. And finally, we're hoping to do some real collects at these other K-band, Q-band, and W-band frequencies. So, and UHF is sitting there. I've got data, voltage level recorded data from 2001. And from 2014, I've got about a megahertz of data. It's not fully continuous. It's when we were running our radar system, but it's about 1,000 hours a year. And so there's a historical record there that could be analyzed. Thank you.
All right, thank you. Tom, you're up last. Last but not least, we're going to hear about some efforts at the center to employ the data that's being collected in order to engage students in learning and competition.
All right, thanks. I'll try to be quick, standing between you and group photo and lunch. So we're trying to close the loop here, basically. We've heard talks about how to collect the data and things and how we're going to use it. And the data competition is actually one kind of a venue that we're trying this. Let's see here. Green button? Okay. All right. So, we, most of you probably have heard about the student data competition that we've been running since late last year. And the purpose of that, competition was multifold. We were hoping to, from a technical point of view, to put out there that, we encourage students to try to develop sensing algorithms, detection algorithms for 5G-like incumbents in the band of interest for us. To go with that, obviously, another important thing here is that we wanted to really have this down in real-world data set, not just in your simulated data set. I think that's where the true value is for the whole exercise. We wanted to basically get students to be interested in this venue, engage students with the data that we have. Hopefully, they're going to be playing with it and find something interesting and fun. And lastly, along the way, that we gradually realized that the data that's been collected, we're going to have to label them. So it's also a good exercise for us to basically get data ready, maybe potentially future release to the community. So here's the design. Essentially, the entire competition runs through multiple phases. We basically have the registration and team formation at the very beginning. That runs from early November to somewhere early in the middle of December. And every team can register up to 3 students. We don't want too many students to work on that, so it's going to be a bigger group for them to manage. And this is limited to the U.S. institutions for our first edition. And then after that, we release the data set. By the way, during the first phase also, the team behind the scenes are basically, working really hard to get the data ready, because, we have hard deadline once the teams are formulated. We want them to have access to the data. We released the data on December 22nd using our SDS system, which is kind of a no small feat. It's the first time that we're trying this, getting data ready and putting on the SDS and for external users to use them. And the data set essentially is comes from labor IQ data plus some documentation that the team prepared. The phase 3 obviously is the students start getting the data, getting the documentation, they have access to the data, they start developing their algorithms. And we as a team, again, behind the scenes, developed a leaderboard system, essentially, along the line of trying to evaluate what the students can use to see how their algorithms perform. The leaderboard turned out to be a really good feature. We'll talk about it more probably shortly. It allows basically the student teams to submit their algorithms to this leaderboard and see their rankings almost instantaneously, comparing against the other teams, knowing some key kind of performances that of their algorithms, working on some behind-the-scenes data set. And the final submission, they can actually do this multiple times to refine their algorithms, but the final submission is March 31st, where we kind of freeze the code and ask the team to basically submit a report also. After that, the team again huddled and look at the reports. We run actually their submission codes behind the scenes on a hidden data set that will generate a second set of accuracy and speed, this kind of metrics. And then we're going to combine both of them for the evaluation. The winner will be announced in a couple of hours. And the committee, I put the note here, basically I'm the lead of that, but we have 3 other faculties from the SpectrumX team who are working on this. So the data set, I don't want to go into too much detail. This is actually the VLA data set that Ali just talked about. So we kind of took that data. Maria's team did a lot of the heavy lifting behind the scenes on labeling those. I want to just mention one thing, the data set split. So obviously we have a training data set released, that's data set 1. This is during the very early stage of the competition. And then we have testing data set 1. This is the second data set that is used in the leaderboard. So essentially when the student teams submit their solutions, they're going to be, the solution will be run using that first test data set. And then there is a second test data set, which is a hidden one. This was not basically given to the student or tested when they submit their solutions. This is just, in the case that, because for those of us who are really kind of curious about this, you could potentially submit multiple algorithms and try to, look at, essentially try to probe the testing data set to see what the features they may have in there. That, we don't want that to happen. So we want to basically have a hidden data set where the student teams never have access to, not even testing their algorithms. So we keep that in our pocket, basically, and then, test the student algorithms using that as part of the final performance metrics. Here's a link for the dataset host. This is the SDS systems that we'll talk about. I'll comment on this a little bit more towards the end. Some statistics. We have 37 registrations by the deadline. This comes from 25 institutions, and in aggregation we have 83 individual students registered. That's honestly is a surprise to us. So thank you all for participating. Out of the the 83 students, 51 are graduate students, 32 are undergrad students. This is another thing I want to highlight. We have a pretty robust participation from undergrad students. As we'll actually see, again, don't want to say anything about the words. We turned out to have some very interesting submissions from undergrads. We'll probably see that a little bit more later today. The participants mostly heard about this through the faculty emails, so a lot of faculties from the center helped us get the word out, and that reaches the students. We also have these social media platforms, word of mouth, and that also attracts some other students. I put a kind of a list of institutions here so you can just take a look. So the results, we're getting some of the technical details here. So essentially, we have 2 categories that we want to award students. You will see that again this afternoon. The first, obviously, is the overall award. Basically, this is based on pure, objective metrics. We look at basically 40% of the weight goes to the performance on the open data set that every student teams can see from the open leaderboard. There is another 30%, obviously, is on this hidden data set in our pocket that we are actually rank all the algorithms in terms of their performances on here. Here, the performance, I really just meant the accuracy performance. And then lastly, we put 20% on the speed, basically how efficient your implementation is in our common platform. Some run really fast, some run a little bit slower. As you can see here, The V1, V2 here correspond to the open and hidden data set. Execution time is really the speed indication. The PDF score is essentially the innovation. We read actually the reports. This is just a snippet of some of the results. This is the top results. Obviously, we have more than this. So just one thing to notice here is that the accuracy really is pretty close, from top to at least the top 5, 6 submissions. In terms of execution time, there's some variation. I'll have a comment on that as well later. So some key observations here. In terms of the algorithmic approaches, we look at the reports, we look at the submissions. Most of them are using, some probably your common deep learning approaches, CNN, estimate, transformer-based. The interesting thing from some of the top kind of submissions are that they really need to do some more, you may say some hardcore or old-fashioned signal processing before you actually put the neural network to work. So that's really separates the top submissions from the others. I think one lesson we learned from this is that it's not just unique. Machine learning is probably a tool that you want to use, but it's probably not the only tool that you want to use to solve these type of problems. The domain knowledge and the things that we have learned in your undergrad and grad courses are very useful to get you a better performance. Let's see here. We have some kind of a, as you can see, the accuracy really plateaued at the 85, 89%. This is something that's very interesting that we really want to kind of get deep, dive into. The performance in terms of speed also has some kind of, variations here. I don't have a lot of time, so let me just see what else do I want to say here. Okay, some of the things we learned really. The real data set is very valuable. This is the first time actually, at least for us, at the center, we've gone through this process of having algorithms developed using real data set and evaluating the real data set. The leaderboard thing is really a significant feature that we didn't actually envision that at the beginning, but it turned out to be one of the defining features, I think, for this competition. We also kind of, important thing is we gained better understanding of the logistic flows. As you can see what's next here, hopefully all things will translate to the next iterations of the data competition. We're thinking about having another one, maybe in the near future. The team is working on summarizing the data set and some paper, maybe writing some articles about it. So I want to just say 1 minute about how we actually make this happen. This is probably incomplete list. I apologize if I missed anybody, but first of all, the students from Maria, Karen, and Ali's groups, really they did the most of the heavy lifting. This is a lot of the behind the scenes work that get data set ready, get the leaderboard ready, handling submissions. At the same time, I want to say give a big shout out to the SDS team. This actually happened because, as you can see in the timeline, it's happening in December last year. It's really the holiday season. So the SDS team really, helped us tremendously during, this is supposed to be a downtime. Everybody is supposed to go home and relax. But because of just the thing that we kind of arranged this, we put a lot of pressure on the SDS team. But they responded, they delivered superbly. Everything actually went extremely well during the submission. We had a little bit of kind of a hiccup, but everything is resolved pretty quickly. A lot of the also students from our team served as external reviewers for the report. And lastly, Emily and Stephanie helped tremendously with the logistics. With that, I'll just stop.
All right, thanks everyone. Thank you, panelists. We have a hard cutoff in 2 minutes, so we really literally have time for one question. So, anyone interested in data or competitions? Oh, gee. All right. Thankfully, I have one. It's lunchtime, don't worry. All right, so panelists, put your never seen my data set hat. What should a new kind of data user do in order to discover your data sets, and how might they begin navigating them in order to figure out if they're useful for their questions?
Yeah, I guess I'll start. So our data is all there in the CCAP data platform. We do have like some kind of problem with labeling. So those those campaigns that we defined doesn't have much label, so we were working on it. So yeah, I guess I let your curiosity guide you on that. So that data is all there in there. So yeah, and let me know if you have any questions on that data set.
Ali, Frank?
I think for all of us, the answer is SDS. So the data is on SDS, so create an account, and if you're on the Slack, let us know to give you access to any particular data set.
Yeah, so we're working with SDS to work on more discovery and search capability, so there is a little bit of that coming along line. Getting an account on SDS is a good starting point. The Haystack SDS is a little closed off for the moment, and we're working to try to get it federated, so you literally will search, and the data sets by class will be discoverable. Now, we do have kind of access control, so there's the ability to have like a closed team data set. You need to know to be in that team or be invited into the team. And that's because there really are sensitivities on some of these data. For example, Ali's experiments, the VLA, the transmissions, one of the reasons we transmit is so that we own the IQ associated with the transmission, and we don't have any legal problems decoding it and making it available. And so you have to be kind of a little bit careful with the low-level data. On the Haystack data, you saw I have a lot of instruments. If you're interested for now, talk to me about things. Not everything is isn't just an automatic yes, unfortunately. And on the other hand, a lot of the data we collected for SpectrumX, our intent is fairly soon to get the Spectrum data on the Haystack SDS, make it openly searchable and available. And even a good amount of the IQ, things that look like astronomy, for example, like I've got maser data, I've got radio star calibration data. It's stuff that is useful from a background labeling and understanding, like, here's something that you can see with a big radio telescope. Look, it's Cas A, and this is what it looks like. Now, astronomers have a lot of data sets like that have been reduced and are in the literature. But we don't have a lot of that as, oh, you can have a machine, just download it and use it and analyze it, and it's got metadata around it. So. And we do have a lot of work improving metadata off all these systems. There's a lot of implicit metadata in all our systems. Even with the MEP, where we did a good job, it's still got a lot of implicit stuff.
All right, let's thank the speakers one more time.